Hi, Jim Heffron. These are my lessons in Calculus 1. So we're working on the homework, and this time it's the homework for related rates. I mentioned when we did the related rates lectures that these traditionally give people trouble, so we're just going to do problems. That's just the most straightforward thing to do is a bunch of problems and keep revisiting them. So that's what we're going to do. Okay, let's have a whack. Let's see then. We're looking at the first problem is number 21 in section 3.3. Of course, I want to go back and revisit previous sections. Here we go. It says f of theta is theta times cosine theta times sine theta. So we'll have a whack. Let's see. Oops. There we go. So I got to take the derivative of theta times cosine theta times sine theta. So it's a derivative of three things instead of two. We have to apply the product rule to three things. Okay, so the product rule for two things, of course, involves a sum of two terms, and in each term, one of the two things has its derivative taken. So here it's going to be the sum of three terms, and in the first term, I'll take the derivative of the first thing, theta. Second term, I'll take the derivative of the second thing, cosine theta. Third term, I'll take the derivative of the third thing, sine theta. So if you take the derivative of theta, I know it's a little bit obnoxious, but I'm going to write 1 times cosine theta times sine theta. Derivative of, for the second term, I'm going to take the derivative of the second thing. So theta times, derivative of cosine is minus sine theta. Derivative of sine is, not taking the derivative of sine, just writing down sine theta. Sorry about that. And then in the last term, I'm taking theta times cosine theta times the derivative of this sine here. Derivative of the sine is cosine theta. Okay, and that's the answer. I suppose that the back of the book probably notices that these two things make a sine squared and these two things make a cosine squared. And so we get here cosine theta sine theta. And then there's minus theta times sine squared theta. And then plus theta times cosine squared theta. And I don't know, you can do all kinds of things to simplify, but I'm wondering if the back of the book won't factor out a theta, and I'm going to just call it done at that point. Cosine theta sine theta minus theta times sine squared minus cosine squared. And again, there's more things a person can do. This is some relationship that you might know, but I'm just going to stop there. Okay, so the major point was the way you take the derivative of three things is to have three terms, where you first take the derivative of the first, then take the derivative of the second, then take the derivative of the third. Okay, great. So on to related rates. So the very first one is question number 3, just really trying to warm up, that's all. Again, this is the Stewart Calculus book. To give credit for credit is due, it's a good book, and they have good questions. So each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? Okay, so of course we're looking at the relationship between area and side length. Area as a function of time is a side length as a function of time. I'm going to call it S of t, quantity squared. Take the derivative of both, you get dA dt is 2s ds dt. Chain rule. And then they go on to tell me, I've forgotten already what they tell me. They told me that the ds dt is 6, and they didn't tell me s, but they did tell me that at the instant of interest, the area was 16, so s must be 4. Okay, so 2 times 4 times 6 is dA dt. All right, so I didn't directly use the information they gave me, but I had to translate it just a little bit, but it wasn't super hard. So that's number 3. Number 13. Actually, actually one of my favorite problems in this section. So a plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour, passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. So it seems to me that we're looking at a picture like this. I've got an airplane. Here's a radar station. It's got one of those big, circular things, and here's an airplane. The plane flies directly over the radar station, and then keeps going. So it says, find the rate at which the distance from the plane station is increasing when the plane is 2 miles away from the station. So it seems to me that I have a picture that has a triangle. I'm going to call them X, Y, and Z. X is given to me as 1. Doesn't vary with time, it's fixed. Then it says Y of t and Z of t. And you kind of have to do a little bit of interpretation here. It says a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles an hour flies directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. So I think that what the author meant is that at the instant of interest, Z is 2. But sometimes I have people read it in a different way to actually be that Y is 2. And I don't think that's a ridiculous way to read it. I'm just saying that I think that I'm going with Z of 2. If you go with Y of the instant of interest is 2, that's not a ridiculous thing to think either. Anyway, what I have is I'm not going to write X of t. I could, it'd be okay, but I'm going to write 1 squared plus Y of t squared equals Z of t squared. If you write X of t there, at some point you're going to find yourself saying dx dt, and then you'll have to say 0. So you've written down something that makes the algebra just a little bit more complicated, but it isn't the crime of the century either. So take the derivative of everything with respect to time. And I've got 2y dy dt equals 2z dz dt. And you can, of course, cancel the 2's and see what we got. So we get, let's see, y at the instant of interest is, and dy dt at the instant of interest is, and z at the instant of interest is, and dz dt is the unknown, I think. Okay, so at the instant of interest, I think we have this picture. Now, if you think the 2 belongs up here in the question, not a question mark, again, I can see how you could read the question that way, but I'm reading the question to be that that's a 2. Okay, so I'm thinking that at the instant of interest, y is square root of 3. Okay, if you read it to be the other way around, that should be a 2, and so that the hypotenuse should be square root of 5. Okay, fine, but that's not the way I read it. So I end up with 2 times square root of 3 times dy dt is given to me as 500 equals 2 times z is 2 and dz dt. And I'll stop there. I mean, you just take out a calculator. Okay, so that was number 13, and then I also need to do 21. Here's, dig it up there. There we go. 21. Here it is. Altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 square centimeters a minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 square centimeters? Okay, so this is about the relationship between the sides of a triangle and its area. All right. So let's see. I think I need a new piece of paper. So it seems to me that I need here something along the lines of area equals 1/2 base times height. Okay, and I mentioned this. I mentioned this while I was, talking about other problems. But you often have to read these questions 2, 3, 4 times. This one in particular, I think if somebody said I just couldn't make out what it was saying, I wouldn't say to them, "What do you mean? You're not paying attention." They're quite terse, and they're often difficult to make out quite what's happening. But I think if you read it 2 or 3 times, you're clearly the question is about area, base, and height, and so the relationship is what I wrote: 1/2 base times height. So most of these problems involve kind of a familiar high school relationship, and then you have to make it dynamic by having it change over time. All right, so let's see. Then I'm looking at take the derivative with respect to time of both sides. So I get dA dt. Again, once I've taken the derivative, I don't bother to write the of t. That's a crutch to help me take the derivative correctly. And then 1/2, and this is a product rule because it's a product of 2 functions of time. So 1/2, and it's going to be b times dh dt plus h times dv dt. Okay, so again, the of t stuff helps me to remember to do the product rule in this case. Okay, and let's see what I can make out by reading the question again. It says altitude of a triangle is increasing at 1 centimeter per minute, so that's dh dt. And area of the triangle is increasing at a rate of 2. Then it says at what rate is the base of the triangle changing, so that's dB dt. And when the altitude is 10, and the area is 100. So they didn't tell me base, but they told me altitude is 10 and area is 100. So let's see, area is 1/2 base times height, and altitude is area is 100. And height is 10. So obviously from that I'm getting that you divide by 10, you get 10 is 1/2 b, so you multiply by 2, you get 20 equals b. So I'm writing in here 20. Oops, off the side of the page. Okay, and as with some of the other questions, I'm not going to actually compute the answer. It's not enlightening to watch me compute values on video. So instead, I'm just simply going to write down the equation, get it to the point where a person should be able to finish it off. Okay, great. That was 21. Now we go on to 37. In all of these, you find yourself either being given a relationship or else having to figure one out from some elementary kind of high school case. Now, the previous question, I was given a kind of a high school formula and expected to know that area is 1/2 base times height. Here, I'm given instead a formula from chemistry. Pressure times volume is a constant, and then asked to figure out at what rate is the volume decreasing at this instant. Okay, so Boyle's law says that when a sample of gas is compressed at a constant temperature, the pressure and volume satisfy the equation pressure times volume is a constant. At a certain instant, volume is 600 cubic centimeters, pressure is 150 kilopascals, pressure is increasing at a rate of 20 kilopascals per minute. So they gave me all the numbers I need, and they also gave me the formula, pressure times volume equals a constant. The previous question, I had to remember that area was 1/2 base times height. All right, so let's see how we do. So let's say here, there we go, back to the right-hand side. Oh, it's the left-hand side. Back to the left-hand side, so it's pressure times P of T times V of T equals not C of T, just C. Okay? And so when you take the derivative of everybody with respect to time, then what you get is this is going to be a product rule because it's a product of 2 functions of time, because I spent some energy, not much, but a little bit of energy reminding myself who's a function of time and who is not. So I get P times dV dt plus V times dP dt equals 0. Okay, the constant doesn't change over time. And let's see if I can fill in the parts. They must have given me enough information. So the volume is 600 cubic centimeters, 600. And the pressure is 150 kilopascals, 150. And the pressure is increasing at 20 kilopascals. So this is 20. And they want to know what's the story with volume. So dV dt. Okay, and again, I'm not going to actually compute the answer, although they do ask, it's a little bit odd. They say at what rate is the volume decreasing, so they might be asking you to ignore the sign, the SIGN. Anyway, we can figure out what is dV dt, and that's all I care about. Okay, very good. So it does seem to me that the major lesson here is that you figure out the relationship between the rates first, right? The relationship between the rates first, and you figure that out directly from the relationship between the quantities. You figure out the relationship between the rates first, and then the last thing you do is plug in. The mistake that people make is plug in too early. If you plugged in the pressure and volume here, you take the derivative and you get 0 on both sides because everything's fixed. So you'd be puzzled. Well, the way not to be puzzled is use the relationship between the quantities to figure out the relationship between the rates. It's pretty intricate here. Anyway, you figure out the relationship between the rates. At that point, you can plug in all the rate information and everything that you have. Okay, very good. Very good.